So I'm David Simmons. I'm one of the other DevRels in Flux, and I mostly focus on IoT, which is, I guess, kind of why some of you are in this room, because it's sort of an IoT track. And I'm going to talk a little bit about digital twins. How many people know what a digital twin is? Great. The rest of you probably won't learn much about what a digital twin is, but that's mostly going to be my fault. So a digital twin is this idea of basically making a replica of something in software rather than hardware, using streaming data from sensors in the real world to create a software representation or a replica of something, right? It's these two quotes I found on the internet, and I'm sorry I didn't attribute them. They were listed with 50 different authors on papers, right? But it's using a digital copy of a physical system so that you can model and interact with behavior basically in a software environment rather than a hardware environment. So why digital twins? It makes a lot of sense for time savings and cost savings, right? I don't have to rebuild an exact model of this hardware system, one in my lab, one in the real world, and then tinker with the one in my lab, right? For those of you that fly on planes, digital twins are actually used by GE and Boeing and other jet engine makers to model the behavior of jet engines rather than tinkering with the one that's on your plane that you're flying in, which I sort of appreciate. So it's a way to innovate in software with basically on physical systems, as long as those physical systems are well instrumented. So things like a Boeing 787 generates about a terabyte of data per flight, and that's just the amount of data that they are streaming from the plane, right? Much more is actually generated and stored on board the plane, which can be downloaded later. So they can actually do a lot of modeling of what's going on the plane while it's flying. They're using these for things like, doing predictive maintenance. They know while the plane's in flight that something's maybe not right and they could use to replace a part, and so the part is delivered to where the plane is going to land, and the part is there, and the plane can be repaired basically during a turnaround instead of having to be taken offline. Right? And they're doing all this by collecting data and modeling that data in software, basically in real time based on sensor data. So this is sort of one of those benefits that people say, what's going to be the good of IoT, right? This is one of the things that's good of IoT. And it really gives an opportunity for innovation and change, because you can now do things based on a software model of a system without having to actually damage the physical system. So what's required to do this? First of all, tons of data, right? As I said, a 787 streams about a terabyte of data per flight. That's a lot of data. And so you really need to be able to efficiently ingest that data, store that data, query that data, and do calculations and visualizations on that data. That's really key to being able to do this, is that highly efficient use of data. So if your database can't handle the ingestion of a terabyte of data over a very short period of time, and then doing real-time querying and analysis of that data, you're not going to be able to take advantage of this, right? And these are all things that we at Influx sort of take pretty seriously about ingestion speed and query speed and storage capacity, because it's really important to being able to do IoT in real time. And one of the really important things about IoT that I say all the time is, if you're not able to deal with your data in pretty close to real time, then you're missing out on a lot of the business benefits of it, right? If I find out after the plane has landed and taken off again that there was a problem with the plane that I could have fixed while it was on the ground, I missed that opportunity, right? Because I'm looking at my data after the fact. So being able to look at that data in real time, do the modeling, do the analysis, and get a recommendation or a solution in close to real time is really key for having this stuff actually work. So in order to do effective digital twin modeling, you really need to be able to do complex calculations on incoming data, right? You need to do correlation of data from multiple data streams and do complex calculations on that data across those multiple streams, right? It's not just one stream of data. It's not just 2 or 3 streams of data. It may be hundreds of streams of data coming in, thousands of measurements with all sorts of different values in all different columns of all of those measurements, and you need to aggregate all of that and do some calculations across it. And Noah did a great job of showing how we can do that in Flux, right? By joining tables and pivoting tables and merging those values into basically other tables that are immediately useful for doing these calculations, right? So that I can do math across measurements, I can do math across different data streams. So I say let's, build a digital twin, and I'm kind of making that up because we're not really going to build a serious digital twin because I don't really have a whole lot of enough sensors to model this entire room. But I do have some sensors. Those of you that saw me sitting out in the lunch area yesterday trying to get all this to work, in order to build all of this, I managed to break absolutely everything over the last week. I broke Flux on my embedded ARM 64 device. I then broke Grafana and the Flux plugin. I managed to break most of my hardware and have to rewrite a lot of that. So I broke everything, and yesterday was build it all again. So up here on the desk, I have a temperature, humidity, and atmospheric pressure monitor. I have an industrial strength CO2 monitor, and I have a particulate monitor, which has actually been really interesting here in LA. Where I am in North Carolina, that really doesn't change much, but it's actually kind of cool to watch it in LA where you have a lot of, PM1, PM2.5, PM10 particulate in the air, right? So the idea is that I can take this data and I can sort of model what's going on in this room. And I'm not going to do a whole lot of that because there's not really a whole lot that I can do that's interesting in that. But what I am going to show is what I can do with the CO2 sensor. So CO2 sensors measure the number of CO2 particles in a volume of air, right? But the volume of that air changes based on pressure and temperature. This is, and I've got these two tables here. It's pretty simple physics, right? As pressure decreases, the volume of air increases, right? But the number of particles dissolved in that air doesn't. And same thing as temperature increases, then there's a subsequent change in the volume of air. So some CO2 sensors actually compensate for this. This one does not. Well, actually it does, but there's a whole other interface that they didn't document and how to do that. So I'm not doing that. So what I'm going to do is I'm going to use my external temperature and pressure sensor to normalize those CO2 values so that I can get a more accurate CO2 reading based on what the current temperature and pressure in the room is, right? And I'm going to do that all with Flux by doing math across measurements. So it may get a little ugly here, right? So here's the basic formula for compensating for temperature and pressure in a CO2 reading, right? It's the CO2 measurement times the measured temperature times the reference pressure divided by the pressure as measured and times the reference temperature. All of these temperatures are actually converted to Kelvin because that's just how the how it works, right? So that's also a lot of fun, right? So I need to pull each one of those parts out of the data that I'm collecting. So I'm going to go through how I'm doing that, and the base calculation is always at the bottom, so you can sort of see where we are in this, right? So I've defined my temperature reference and my pressure reference as sea level, basically, and 25 degrees Celsius as Kelvin, right? And so I'm going to grab my CO2 measurement out of the bucket where I'm storing it, right? And I've got a K30 CO2 reader, and it's storing a value of CO2. And so I'm going to pull that out. I'm going to store that in a table that I'm calling CO2 measurement. And then I'm going to create another table called the temperature measurement. And I'm going to grab the temperature that I'm sensing out of a different sensor and store it in that table. Do the same thing with the pressure measurement. So now I've got basically all the parts that I need, right? I defined the constants that my reference temperature, my reference pressure. I've now collected my CO2 measurement, my temperature measurement, and my pressure measurement, and it's time to sort of pull all that together and do the reference. So first thing I'm going to do is I'm going to join two of those tables together, the CO2 measurement and the temperature measurement. I'm going to join that table with some of the other measurements, so I have, and finally I'm going to join all of that together so I have one table that has all of those measurements in it, right? There's probably a more efficient way to do this, but this is just how I did it yesterday, right? So I've created two tables, and then I've created a third by joining it all together. Now I've got a single table that has my timestamp, shared timestamp, it's got my measured values, and I've got my constants. And then I can go and I can run this calculation in Flux based on that table. And I will get a value that is a compensated CO2 value from my measured CO2 value with my other measured values. So we're going to try to do this live. The speakers net has been a bit of a trash fire this morning, and this is all going out over the internet. So with that being said, it's actually working. Can you guys see that okay? So as you can see up here, the top number is the adjusted CO2 value, and the bottom number is the raw CO2 value. Down here I'm storing the atmospheric pressure and the temperature Celsius. So I'm using these two values to basically calculate in real time the adjusted CO2 value. So I can compensate for any temperature and pressure differences. This would be a lot more fun if I were like in an airplane at, and it was pressurized to 7,000 feet. There would be probably a much bigger delta there in the change. And just for fun, down here, you can see what the particulate matter is currently. And there's a fair amount of particulate matter in the air in LA. Yay, LA. What's the old UCLA joke? UCLA, but only on a clear day? Yes?
What's it normally in South Carolina for you?
I have never seen it above a couple of hundred, right? So seeing almost 1,200 is like, wow, I can eat the air. Now, there are other calculations that I could do based with particulate matter and humidity. And the reason these things would be interesting for doing a digital twin is I can look at how can I adjust various environmental controls in here to compensate for various things. Interestingly enough, we are up at about, just about 1,500 1,600 parts per million CO2. So some of you are probably starting to feel a little distracted. There's a couple of really interesting cutoff points for CO2 that if you measure enough meetings, you start to see things. At about 1,500 parts per million, people start to get a little bit distracted and can't really concentrate as well. At about 2,500 parts per million, people start to get really sleepy and really can't concentrate and start to yawn. And anything over about 4,000 parts per million, people start to complain that the room is hot and stuffy and they need more air, right? And that's because you actually do need more air. There's not enough oxygen in the room. It's typically not hot, it's just there's not enough oxygen for everybody because we keep expiring our CO2. So, in essence, what I've done here is not really, I said I was going to create a digital twin. I haven't really created a digital twin, but what I have been able to do is model in real time, compensating a sensor based on environmental factors in the room, right? Something that I actually couldn't do with the previous versions of InfluxQL because I couldn't do math across measurements. So I wasn't able to do this. I would have had to find a sensor that I could do this compensation inside the sensor and pull that data out, which is in a lot of ways more difficult. So this actually makes my life a lot easier, and it changes what kinds of sensors I can buy because I can now do this external compensation in the data. And I can look at, well, how is this changing and what's changing in the room, and can I, lower the temperature to make some changes. So if you actually want to see the sensors, they're up here on the table. 2 of them are in nice boxes. The particulate one is a brand new sensor that I'm playing with, and so it's like bare wires and a board, and I try not to play with it on airplanes because it makes people nervous. But the rest of them, you are welcome to come up. You can breathe on the CO2 sensor, and you can see the changes go in real time. And I'm happy to answer any questions. That's it. Yes.
So, what's the trigger used for Flux? Is it like per event, per any channel, or is it a time trigger schedule system?
What do you mean the trigger? Oh, the question was what's the trigger for Flux? And I'm not actually I'm not actually doing it. There's no trigger in this. It's actually reading the data out of the database. It's pulling data out, right? So it's how often am I querying? And right now I'm querying every 5 seconds, right?
The query does the math.
Yes, the query does the math. And I think I can show you. Last time see the query seems to have disappeared in here. However, there's the query. So here's the actual query, right? And I went through that in my slides, and you can see the raw results from this query here, right? And it's pulling a lot of data back. If I look at this in I can actually view this as raw data, and you'll see the table that it's created, right? And it's the CO2 adjusted, the measured, and the time. This is the final table that it's created by doing all of these joins, and I end up with this final table, right? And that's all and so it's doing that basically every time the dashboard updates, it's doing a read of the data, it's doing all those calculations, it's building that table, and then it's displaying the results of that. Right? Does that make sense? Okay. Yes?
If you join on time, does the times have to be exact?
Do the times, there's, if you look in here, you can see that I am doing an aggregate window. I'm windowing the data a little bit to align it. And you'll notice that in the Grafana window, it's not aligned quite, and that's because I had to do something interesting in Grafana. This is the beta version of the Flux, and so you'll notice I'm actually doing 2 queries. One gives me the adjusted. Oh, Russ was breathing on my sensor. One gives me the adjusted, and then I run a separate query that gives me the raw reading, right? And those two queries are not time aligned, and that's why there's just a slight skew in this graph, right?
So you basically do have to align the time somehow.
Yes, yeah.
And I guess it depends on the sampling frequency of the sensor.
Excuse me?
And I guess it depends on the sampling frequency of the sensor.
It does, and I know, I built that sensor, and that sensor samples once every second, right? A couple of the other sensors I have sample a little more frequently, but the round trip time on the network to the server that this is running on has been flapping at around, a half second to a full second. As I said, the network's kind of a trash fire today, and there's a fair amount of packet loss. So faster updating isn't really giving me anything. I'm doing the 1 second updates from the sensors, right? Great, thank you. I'm not sure who's next, but thank you.